Hey, let's hit the side splitter theorem. This is how proportions work in parallel lines. And I really like this theorem because it lets artists do their thing. In this cartoon, you can see this idea of depth perception. The artist has used this theorem. And for artists and non-artists alike, you know, you artists think you're so awesome, and you are. For those of you who are non-artists like me, you can feel a little artsy if you know this theorem. This picture here of the light poles, this is an example of what's called one-point perspective. Like if you were here at one point, you draw lines out from there, like here in the road, then you can make things look like they're going out of the page. And the neat thing about this, or the geometry, is that all these lines here, these poles, they're all parallel. And so what does that mean? Well, that means that we'll be able to figure out some distances in these proportions that they form, like this 0.5 inches compared to the 0.42 inches. That's proportional to the 0.57 over the x here. So that's awesome. Let's get mathy about it, like how I did this mathy. I think I'm funny. Nobody gives me enough credit for that funny stuff. Anyway, here's the theorem. If a line intersects two sides of a triangle and runs parallel to the third side, so let's see what we've got here. We have MA is parallel to TH. Those are parallel. Then, well, what do we know? Well, we know that the sides, this MY, if we compare it to this YH, that's proportional to the other sides, AT and TH right here. So it splits those two sides in a proportion. So the other two sides are divided proportionally. Divided proportionally. So how's that written? Well, that means that MY is to YH, there's my one side, as AT is to TH. Like all proportions, you want to stay in the consistent order, but that's it, and that lets you solve other problems, so it's pretty cool. All right, let's see how it works. So we're going to find the value of x. First, check to see, do you have your givens? We've got parallel lines. Those are parallel. So we see that these two sides are divided in proportion. That means 8 is to 3 as 12, staying consistent, 12 is to x. And you know what to do from there. 8x on the cross multiply would equal 36. And dividing that by 8, we're going to get 4.5. Of course, you say, well, that's easy, Mrs. Pryor. How about a tougher one? Well, here's a tougher one for you. Here, let's just start it out like we did before. We've got our parallel lines, so these sides are going to be split proportionally. That means this 4 right here is to this length, but that length's not given. Can we figure it out? I think we can. Let's take 4 from 24, the whole thing, so that means this piece is going to have to be 20. So 4 is to 20. 4 is to 20 as this piece, which is missing, is to x plus 16. I don't think that 30 is really going to help me figure that out. Shoot, okay, I'm going to have to try a different approach here. Let's see. We can do this different ways. So how about we try, let me start over. How about we try 4 is to 24, the whole thing. 4 is to 24. So that's 4 is to 24 as, shoot, I'm still missing this and I don't know how to figure it out. All right, maybe third time's a charm. Let's see. All right, how about we do use what we know? So we know this is x plus 16 and we can compare it to this whole length here. So let's start with that. X plus 16 compared to 30. What would that equal? If we're going to be consistent, we would take the same side over here, which we figured before was 20, and compare that to the whole length 24. Now we are in business. It's to 24. Okay, sometimes you got to try a few different things to get a matchup. All right, let's check out our cross multiply. Taking 24 and timesing by the whole quantity, x plus 16, set equal to 30 times 20. Okay, distribute 24x plus 24 times 16 is 384. And then that equals over here, that's going to be 600 in the product. Subtracting 384 will leave me 24x. And I'll bring that 600 down to 216. And our final step in dividing by 24. 216 divided by 24 gives me 9. If I can write it. Okay, so x is 9. Whew, that one was tricky. Let's see this next theorem. Now this is actually a definition for you. We're going to lead it into a new theorem. It's the midsegment of a triangle. Some of you did a little extra credit a while back and got this already figured out, but a definition, the midsegment of a triangle. If you look at your picture, DE is the midsegment we're talking about. And the reason it's a midsegment is because it connects the midpoints of the sides. D is a midpoint of one side, E is a midpoint of the other side, and when we connect them up, we get the midsegment right there. So it connects the midpoints, I'm abbreviating that, of two sides of that triangle, making it the midsegment. Right there. Every triangle has how many midsegments? Well, there's one of them. The thing is there's another side and I have another midpoint. Let's say I'm going to have to estimate this right about here, and we'll tick mark that. That's the midpoint of my third side. So if I connect endpoints here, and we'll call this F, DF is a midsegment, and then right there, EF is a midsegment. So there's actually 3 midsegments. 3 midsegments in every triangle. Now, one of the things about midsegments is that, well, 2 of the things. Number 1, it's going to be parallel to one side. So this midsegment DE, you can show that that is a parallel to that AB side. And the other thing is that's half of its length. What does that mean? That means that half of the length of that long side AB is equal to DE. It also means, if you switch that around, that AB is equal to 2 lengths of DE, or 2 times DE. So just some sample numbers. If DE is 8, AB is twice as long. A would be 16. That's the midsegment theorem. And it's based on those parallel lines. So here's an example of a typical midsegment kind of question. You're going to find these measures. Notice they've got midpoints marked all 3 sides. So that makes DE a midsegment. And they want to know how long it is. How long is this DE side? Well, if we look to the third side of the triangle that it's running parallel to, we can find a measurement of 15. So to find DE, that's half of 15. We just got to cut it in half, 7.5. That's DE. That's number 1. Now number 2, DB. DB is this segment right here. And what information can help us find that segment? Well, I would notice that it's the same length here, since that D is a midpoint, and there's the midsegment that helps me, that 9.2. That 9.2 can be transferred right to here and to here. Does that make it twice as long as the midsegment? I think it does. So DB would be 9.2. Let me back up and put that 7.5 up here as an answer. Finally, what is an angle? They're wanting an angle measure, FED. I can't even find, oh, there's F, I covered it up. FED, what's this measure here? That angle rotation. Well, let me see, that's an angle, I only have another angle here of 82 degrees, and maybe that'll help me, I think so. Let's see, I've marked it in red, but let me come up and notice this Z I'm making. Z's make alternate interior angles, and if they're parallel, which they are on this midsegment, then those are going to match. And so that angle would be 82 degrees to match the one that was given. Cool stuff. All right, a couple more corollaries to the side splitter theorem. These are theorems that are easy to prove, basically. Let's read through this one. If 3 or more parallel lines intersect 2 transversals, let's check out the picture. There's 1, 2, 3 parallel lines, and the 2 transversals are coming through those. Then the transversals are cut into proportional parts. Proportional parts. It's like a tongue twister. Okay, so that means that AB and the other part down here, BC, those can be in a ratio, and they're going to be equal to, if we come over to the other transversal, FG to GH, staying consistent with the order, GH. All right, awesome stuff. This is a typical example. Find the value of X. Well, some people would say, here it is, right here. Of course, that's not what we're doing. We're going to find a number. Okay, so what can we set up? Let's see what we've got. So I could go 3 is to X. 3 is to x, kind of working backwards here, as what is to what? Well, I would have to know this part because I used the 3, so I have to match it up right there, is to 4. Well, that part's not too hard to figure out. They told us the whole thing was 6, so if that's 4, that's going to be 2 to make a total 6. So 3 is to x as 2 is to 4. That means on a cross multiply, 2x is going to equal 12, and x is divided by 2, 6. X will be 6. That's the side splitter theorem. All right. And then one more corollary, the side splitter theorem. Corollary number 2. If parallel lines cut a transversal into congruent parts, so let's see what's happened. Here's some parallel lines. Here's our transversal, and it chopped it into 2 congruent parts. They're equally spaced. Then they will cut any transversal into congruent parts. So that means I could add more transversal lines. Let's add one right here. Coming any direction I want, that transversal line is also going to get cut into congruent parts. So these are going to equal each other as well. And that'll work no matter which way you draw your transversal line. One more just for fun. If I draw it straight down like this, then 1, 2, 3 matches 1, 2, 3 right there. That's one of my favorite theorems. I like that one. All right, here's the last example. We're going to find the value of x. First, check it out. You've got these parallel lines, and here's a transversal that's been cut into equal parts. You can notice those congruent tick marks. So if that transversal got cut into equal pieces, then this other transversal here is cut into equal pieces. That means we're able to add tick marks here of our own. So if you want x, you need to know that this segment is congruent to this segment. We're just going to set them equal. X plus 7 is the same thing as 20. That means x is going to be 13. That is your side splitter theorem. And that's pretty awesome. That lets you do some perspective drawing. I love this stuff.